Hello students, and welcome to the lesson on special right triangles. And we have our first theorem here, which states, let me zoom in here so you can see what it states, that in a 45, 45, 90 triangle, the hypotenuse is the square root of 2 times as long as each leg. Okay, so the hypotenuse is square root of 2 times as long as each leg. And we can illustrate this the following way by saying that if you have a right triangle, and one of the angles is 90 degrees, of course. You have a side that's 45 degrees, this side that's 45 degrees. I will call this the hypotenuse, and I will call this A is the leg. And notice here that this is 45, 45, so it's an isosceles right triangle. So I'll also call this length here A. So what the theorem says is that H is equal to the square root of 2 times A. H is equal to the square root of 2 times A. Okay? And we can prove this theorem in a fairly straightforward manner. And the way that we prove this, and we are actually going to prove this, okay, is using the Pythagorean theorem. So we can say, look, a squared plus a squared is equal to h squared. And this is just using the Pythagorean theorem. Okay. And 2a squared then is equal to h squared. This is combining like terms. And now if I wanted to finish this and solve and get get h entirely by itself, what I would need to do is take the square root of both sides. So take the square root of both sides there, and that would leave me with square root of 2, square root of 2 times a is equal to h. Okay? So this is combine like terms. I'm giving my reasons here. And then we're just taking the square root of both sides. And so there you see it. You see that h is equal to the square root of 2 times a. And this is true for every single triangle that is 45, 45, and 90. Now let's take a look at another theorem, which says this is the 30, 60, 90 triangle theorem. And it says that in a 30, 60, 90 right triangle, the hypotenuse is twice as long as the shorter leg, and the longer leg is square root of 3 times as long as the shorter leg. And a lot of times, you know, when we work on this, it's easy to get lost in this theorem just because we don't quite know what it says. I mean, we can't prove anything unless we know what it says. So let's draw out this triangle here. This is 90 degrees. Let's make this one 30 degrees. We'll call this side A. Make this angle up here 60 degrees. We'll call this side B, and we'll call this side H for the hypotenuse. And what the theorem says is that the hypotenuse is twice as long as the shorter leg. So the shorter leg is A, so the hypotenuse is equal to 2a, and that the longer leg is square root of 3 times as long as the shorter leg. So the longer leg, which is b here, is square root of 3 times as long as the shorter leg. So b is equal to the square root of 3 times a. Okay, so that's what this theorem says. It says two things. First is that the hypotenuse is twice as long as the shorter leg, and the longer leg is the shorter leg times square root of 3, and always. Okay, that's always the case. So this is really one of the fundamental theorems of trigonometry. Everything else in trigonometry, it seems, is driven by this. And to prove this, I'm going to use my my whiteboard here because I'm going to need a little bit more space. If you need some space, just do this proof on a separate sheet of paper. Please do not try to squeeze this all on here because it is very, very important that we get this proof correct. So this is not 45, 45, 90. This should say 30, 60, 90. 30, 60, 90. Okay. And I'm going to reference back and forth what we were talking about before with the lengths of the sides. So I'll draw this picture here. I know that this is A, this is B, this is H, 60 degrees, 30 degrees, okay, 90 degrees. And we want to show that H is equal to 2A. So let's show that first. And one of the tricks that I'm going to use here is to make a duplicate of the angle. So I'm going to make some names here for these points, D, E, and F. Okay. So the first thing I'm going to do is to duplicate triangle DEF, and duplicate here really just means taking this and I'm going to extend this out a little bit, and I'm going to construct this line here, okay? And I'm going to call this new point here DEFG, okay? So now I have a new triangle, triangle triangle GEF. Okay, triangle GEF. And I'm going to make it so that this line here is congruent to A, this segment here is congruent to H, okay? And of course B is congruent to itself. And so you can see here that by doing this, triangle GEF is really congruent to triangle DEF. And I'm going to make a note on the side here. I don't have room to write all the theorems, but the explanation, but this is the ruler postulate and the protractor postulate, which says that I can replicate any length and any angle that I need to replicate, basically. And I replicated it here so that I have two different triangles that are sharing a side. And when I do that, one of the things that we know is that this angle here must be 30 degrees, and this angle here must also be 30 degrees. So now I'm going to look at the bigger triangle. I'm going to look at this triangle, the bigger triangle, DGF. So looking at triangle DGF, I have a 60-degree angle, 60-degree angle, and this one right here is 30 plus 30, so that's also 60. So this is an equilateral triangle. Equilateral. Okay. DGF, the big triangle here, is an equilateral triangle, which means that, well, this side here is also H, and this length right here is also A, but the combination of the two lengths is H, since the sides here are all equal to H. And you can see from this picture now that DG is equal to A plus A, or 2A. You can also see that DG is equal to H. Therefore, we can use the transitive property and say that H is equal to 2A. So this is the transitive property. And there we have it. That completes our proof of the first part, at least. This completes the first part of the proof here is that H is equal to 2A. Okay? H is, in fact, equal to 2A. This little box here, I see this in a lot of math books. It means we're done with that part of the proof. H is equal to 2A. And that's a very important idea. Okay? That the hypotenuse is just twice as big as the shorter side. Now, this picture is a little bit cluttered, so I'm going to reproduce it down here, the original triangle. And now we're going to try to show that B is equal to the square root of 3 times A. Okay, so I want to show that b is equal to the square root of 3 times a. Okay? I have 60 degrees, a, b, h, 30 degrees here. And one thing we know already, we know to be a fact, is that this h is equal to 2a from part 1. So this is kind of an interesting theorem where it's two parts, but we're actually going to use one of the parts to prove the other part. So now, we can just use the Pythagorean theorem. And we're going to use the Pythagorean theorem with the understanding that we're trying to eliminate h. We want the relationship between b and a to exist. Okay, so we're going to use Pythagorean theorem, and we're going to need to eliminate h from the equation somehow. So let's use the Pythagorean theorem. A squared plus b squared is equal to h squared. Okay. But we need to replace this with some expression of a or b, and we have it right here. This is eliminating is very easy because of what we did in the last part. So a squared plus b squared is equal to quantity 2a squared. And again, I can't stress this enough how often students forget that this is a quantity squared. And so we get a squared is a squared plus b squared is equal to 4a squared. Then we can do subtract a squared from both sides. We get 4a squared minus a squared. So b squared is equal to 3a squared. And we want to get b by itself, so we're going to take the square root of both sides. And you can see here that b is equal to the square root of 3 times a. And there you have it. This ends our proof. And here we didn't have to do anything complicated with the picture. We just used the result that we learned from part 1 of the proof. And I didn't really give a whole lot of reasons here. It's just the Pythagorean theorem, and the rest of this is algebra. And so there you have it, the proof for the special right triangles. And now what we're going to go on and continue to do is try to write some ratios using the special right triangle, the special triangles. All right, so now we're asked to fill in this table. I have a list of theta across the top: 30, 45, 60, and then a list of all the 6 trig ratios. And so in here, what we're looking for is what is the sine of 30. You know, so this is the sine of 45. This is the sine of 60, okay, and so forth. Okay. And again, for these types of problems, it is tremendously helpful if you can draw out a picture of these triangles. So I'm going to draw out both of these triangles. First, the 45, 45, 90. So this is the 45, 45, 90, and that's going to help me answer basically all of these numbers here for 45 degrees. And I know that this is A, and this is square root of 2A. Okay. Then I'm going to draw out the 30, 60, 90 triangle right here. I know that this is A, this is 2A, and this is square root of 3A. Okay, so that's going to help me fill out everything in the third column and the first column. So let's start with the sine here, and let's do sine of 45. Whoops, this should be square root of 2a. Sine of 45 degrees is just opposite over hypotenuse, so that's a over square root of 2a. And you can see here that the a's will cancel, so that's 1 over the square root of 2. But we need to rationalize this, so we need to multiply it by square root of 2 over square root of 2, and that gives me square root of 2 over 2 as my final answer, okay, for a sine of 45. Now I'm going to switch to a colored pen here so you can see better, but it is highly advisable that you do not do this in pen. I'm doing this only so that you can see clearly on the video. let's see what we have for the sine of, oh, I forgot to label this one. This should be 60, this should be 30 degrees. Okay, that'll help us a lot. Sine of 60 degrees, sine of 60 degrees. So 60 degrees is here. I have it's the opposite over the hypotenuse. So that's square root of 3a over 2a. You can see that the a's cancel, so that gives me square root of 3 over 2 for sine of 60. For sine of 30, if I use this 30 degrees here as my reference angle, I have a over 2a, that's the hypotenuse, and that simplifies to 1 over 2, or 1/2. Okay. I'll do a few more of these. Let's see, cosine of theta, so we're looking for the cosine of 30 degrees in this case. So if I use this, cosine is adjacent over hypotenuse, so that's square root of 3a over over 2a, which is square root of 3 over 2. And at this point, it is highly encouraged that you pause this video, take out a pencil, and try to fill in the rest of this by yourself, and then hit play again so you can see my answers. But I'm going to continue here. Cosine of 45 is a over 2a, a over square root of 2a rather. That is 1 over square root of 2, which once we convert it to simplest radical form, square root of 2 over square root of 2. Cosine of 60, we have to look at this triangle. 60 is the adjacent, so that's a. Divided by the hypotenuse, so that's 2a, which simplifies to 1/2. Okay, how about the tangent here? So let's look at the tangent of 30 degrees. So tangent of 30 degrees is the opposite over the adjacent. The opposite is a. The adjacent is square root of 3a. So that gives me 1 over square root of 3. But remember, we have to rationalize these denominators. So we're multiplying by square root of 3 over square root of 3. And as my final answer, I think I've given myself just a little bit less space than I need, but this is going to give me square root of 3 over 3 as my final answer for the tangent of theta. Okay. Let's continue here. Now I'm not going to rewrite the angle here just because it's a little hard because I can't fill all this in, but tangent of 45 degrees is opposite over adjacent, so that's a over a, which equals 1. Tangent of 60 degrees is square root of 3a over a, so that's opposite over adjacent. That gives me square root of 3. Now, these next ones are kind of hard, or at least a little bit tricky if you haven't done this before, because what we have not dealt with before is special right triangles with the cosecant, secant, and cotangent ratios. So let's start with cosecant, and remind yourself that cosecant is the reciprocal of sine. Okay, so it's the reciprocal of sine. So that's hypotenuse over the opposite side. This is hypotenuse over the opposite side. Okay, so looking at the cosecant of 30 degrees, the hypotenuse here is 2a, and the opposite side is a, so that comes out to 2. And we can also compare these two right here. The sine of 30 is 1/2, so the cosecant of 30 should be the reciprocal of that, which is 2. How about the cosecant of 45 degrees? So that's the hypotenuse, square root of 2a over the opposite side, which is a, and that simplifies to just square root of 2.
Good day.
Thank you. Have a good day too. All right, now the cosecant of 60 degrees. So I'm looking at this 60 degrees here. The hypotenuse is 2a. The opposite side is square root of 3a, and that gives me 2 square over the square root of 3. But I have to rationalize this denominator, so I have to multiply the top and the bottom by square root of 3, and that gives me 2 square root of 3 over 3, okay, or 2/3 square root of 3. Let's continue here. Secant is the reciprocal of cosine. Secant is the reciprocal of cosine. So if I can highlight this, maybe that'll help us see this a little bit better. Sine, okay, goes with cosecant. And then cosine actually goes with secant. So cosine goes with secant. And of course, cotangent goes with tangent. So for the cosecant, let me switch my marker here to a different color. So secant is hypotenuse over adjacent. Okay. And I can look at the picture, or I can also just take the cosecant here, or the cosine, and just flip it. So this is 2 over square root of 3. And to see why that is, this is cosecant, this is the hypotenuse, okay, of 30 degrees, so that's the hypotenuse, that's 2a, and the adjacent side is square root of 3a, which again just reduces down to 2 over square root of 3, but I have to rationalize this denominator, so I've multiplied the top and the bottom by square root of 3, and that gives me 2 square root of 3 over 3. Okay. Let's keep going here. Secant of 45 degrees is the hypotenuse over the adjacent side. So that again reduces to square root of 2. Secant of 60 degrees is the hypotenuse, 2a, over the adjacent, which is a, and that gives me 2. And finally, cotangent. And again, cotangent is just the reciprocal of the tangent function. So cotangent and tangent really are just reciprocals of each other. So cotangent tangent is opposite over hypotenuse. No, opposite over adjacent. Sorry, opposite over adjacent. So this is adjacent over opposite. Okay, that's adjacent over opposite. So cotangent of theta is, when theta is 30 degrees, cotangent of 30 degrees is adjacent, square root of 3a over the opposite a, so that reduces down to square root of 3. Okay. And again, I could have also taken this number here and just just flip that, and I'll get the same thing. Cotangent of 45 degrees is adjacent over opposite, so that's a over a. And for 45, it's really nice because it doesn't really matter which one, the adjacent and the opposite are the same thing. And finally, for 60 degrees, the adjacent is a. The opposite side is square root of 3a. That reduces to 1 over the square root of 3. But we have to rationalize the denominator. So then that gives us square root of 3 over 3. Okay. And I'm going to sort of box all of my final answer here so that it stands out in all of the clutteredness here. Okay, so you can see more clearly all of the final answers. There's some work to be done there, and I also recommend that you recreate this table without all of the cluttered work that I have here. Okay. We'll even box this one again. That's square root of 2 over 2. And so there we have it, three angles of the special triangles, 6 ratios, and that gives us 18 different ratios that we need to learn. And you really should try to internalize all of this. You know, again, you're going to drive yourself crazy if you try to memorize everything. But what you really need to do is just memorize the triangles and understand the definitions of these, so that when you're given any one of these ratios, you can fairly quickly calculate or deduce the answer, and without using a calculator, using purely just your knowledge and your ability to convert everything into simplest standard form. Okay, and I'm going to end this video here because it's getting a little bit long, but we will continue this to another video where we discuss how to use this table to answer questions.